We are live on YouTube. तो भाई स्टार्ट कर दो। उत्तम भाई स्टार्ट कर ही दो। उत्तम भाई यू आर नॉट ऑडिबल। કિશન
હા બોલ.
ઉત્તમ ભાઈ બોલે છે તે સંભળાય છે?
ના ના
એમને ફોન કરીને કે ને. અને અવાજ કેમ ફાટે છે? દિલીપભાઈ ઉત્તમભાઈ બોલે છે તે સંભળાતું નથી.
ના નથી સંભળાતું. મને લાગે કિશન સ્ટાર્ટ કરે.
હારું કિશનને કહી દે.
તમને પ્રોબ્લેમ લાગે છે ત્યાં. Okay, so I welcome you everyone. आवाज आ रही है?
આ રહી है.
Hello?
Yes, Kishan, yes, you are audible.
Yeah. So I welcome all of you for today's presentation. Today's presentation is mainly on seeing the unseen, that is using the cloud chamber experiment, which will be presented by Mr. Jay Patel. This program is conducted by the Universe Science Forum. We are a group of people who uh, work to increase awareness among common people about the science and its activities. We do many type of activities like showing experiments in schools. We also has our e-magazine called Vignan Chetna, which is a monthly e-magazine. Other than that, we also do this type of webinars every month, and I hope you enjoyed this one too. And I would like to introduce our today's presentation presenter. I'm very glad to introduce our today's presenter, Mr. Jay Patel. He is currently studying in third year of his bachelor's degree in physics. He has very deep interest in experimental physics, especially, and he has recently stood third in all over Gujarat for National Anvesika Experimental Skills Test. Other than that, he has worked as a research intern at Institute for Plasma Physics, Gandhinagar, working on X-ray fluorescence. He is also receiver of famous Inspire Scholarship. Apart from this, he is a fabulous writer. He writes poems on physics and other sciences on our e-magazine Vignan Chetna monthly. I can go on, but we have less time, so I will stop here. but his presentation will give more elaborated version of his information about his personality. Over to you, Jay.
Yes. Thank you very much, Kishan, for this introduction. Now, am I audible? Can anyone tell me, am I audible clearly?
Yes.
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 Yes, yes.
Okay. So, firstly, I would like to give a sincere thanks to all of you for joining me today here. Good morning to my dear friends and professors and respected elders. This is uh, this is for first time for me to give a talk like this, and I hope it would not be a boring talk. I will try to entertain you and give at the same time provide some glimpse of nuclear physics and particles, and I will try my best to make it more knowledgeable. Some you can ask me questions at any time in the between the talks, as I want to make it more interactive. So you can ask me questions, but it is in my humble request that if you please unmute your mic only when you want to ask the question or you want to talk. And so I will start with the overview of the talk, how it will be proceeded, and what things I will present in my talk today. So firstly, I will give I will talk about the history of how these chambers were discovered, how invented, how it was proceeded, what scientists how it worked, and how the central idea of detecting the particle came, from where it came, how it came. And then after I will talk about the working of this model, how it works, what are the principles of the working of this chamber, and after that I will uh, give you the information about how I made my cloud chamber. What was the apparatus I used, how I managed it, what was the procedure of it, and then lastly I will give you the about the results and observation idea about results and observation. What were the results obtained? What were the observations and other things? And then I will conclude my session. So I will start now. I hope you all can see my PPT. One of you can unmute and tell me if it is visible.
Yeah, it's visible.
Okay. Thank you, Keshav. So, seeing the unseen, the cloud chamber experiment. The heading is, I think, appropriate for this experiment, as we are seeing something which has been talked a lot in our high schools, that there is electron, there is alpha particle, there is this particle, there are protons, beta electrons, and that all this stuff. But we haven't seen it because our eyes are not that capable of seeing those minute particles, nor we can see with microscopes. But we need a different type of instrument for doing that, and that is what the cloud chamber is, and that is also discovered by by it is not a purposeful discovery. It was a लाइक कुछ चाहा कुछ और हो गया कुछ और, लेकिन हुआ वो बहुत अच्छा हुआ। तो वो बोलते हैं ना, जो भी होता है वो अच्छे के लिए होता है, वैसा हो गया था। तो आई विल स्टार्ट विद द स्टोरी ऑफ हाउ इट वाज डिस्कवर्ड। सो दिस वाज द साइंटिस्ट CTR Wilson. He was a Scottish physicist who discovered or invented this particle chamber. He was working in 1894. He was working as an assistant observer in meteorological observatory, and since then it was on mountain tops, Ben Nevis Mountains in the Cambridge, UK. So at there he used to go to that observatory and take observations of different phenomena in atmosphere and in skies and all these things. So once at a time he noticed something very fascinating. When he was standing on the mountain, he see the very colored rings around the sun, something like that. This. So saw this and he was much fascinated, and at the same time he was very mystified. So how it came, what is the phenomena of occurring like this? These are particularly halos which are created in the atmosphere due to refraction of light with certain size of crystals of. And by seeing this, he was very much fascinated, at the same time mystified. He decided that I would make an atmosphere in my laboratory, and to mimic this I will make atmosphere to mimic this, and want to study that how it is created and what are the phenomena occurring that there. So he created a he when he get back to Cambridge, he started making models and all that. He invented, or he made this type of model, which was later called as a Wilson cloud chamber. He wanted to study the atmospheres. He wanted to make atmospheres, but he ended up doing something else, which was more extraordinary than what he has thought of. So this is the Wilson cloud chamber. You can see here that this is the region where the particles should be detected. This was the active region here. There is a piston here below, which is by which the piston is by piston the chamber is diaphragm is pulled, and it volume is expanded. As the volume cools down, the pressure decreases, and the water droplets, the water vapor which is used here, detects the particles upon condensation. I will explain later how it all goes. The principle is same, but the chamber that I have made is a different one. That is a upgraded version of this. That is a diffusion cloud chamber. But this was the very first cloud chamber which was made, and based on these principles of detecting particles, and all these upgradations were made with time. This all thing happened in between 1920s to 1950. So this was the wonderful era for nuclear physics. Manhattan projects and these particles and many more discoveries were made in this nuclear physics. And if you see that the many Nobel prizes were also given to the scientists for their discoveries. We will particularly see here which Nobel prizes were won with these discoveries and what was the benefits to humankind. So you can see this was the first version of cloud chamber. Now, Ernest Rutherford used to say, based on the applications that this cloud chamber made, uh, brought to see the physics to the nature. And he used to say the most original and wonderful instrument in scientific history. This was given by Ernest Rutherford. This is a statement. You all know Rutherford, who is the guy who with alpha particles. Not he is not alpha particle emitter. Of course, there is a source, americium. But so this was the heading he gave. Now the invention of the cloud chamber was not less than a revolution, as I discussed nuclear physics. Physics works. You can see things happening in front of you. So that was the cloud chamber. Now the scientist which get a Nobel Prize on some upgradation was this Patrick Maynard Stewart Blackett. He won the Nobel Prize for upgrading the cloud chamber. He attached Geiger counter, which also it is also one kind of cloud chamber, is particle chamber, sorry, particle detector. And with cloud chamber, he attached it to Geiger counter in such a way that it photographs the particles. As soon as the particle passed through the chamber, it automatically photographs. So it was a wonderful experiment by which the photographs were captured, and it was a kind of very efficient work done by him. He also did a great particle discovery. Particles, not he also did some good work in nuclear physics and cosmic rays detection and all this stuff. He also proved the Carl Anderson discovery. The Carl Anderson was another physicist who was also offered a Nobel Prize in 1936 for the discovery of positrons. You have heard about this, you have seen this photo many times, I guess. It is a very famous photo. The lead plate is there, and by gamma, a scattering of the gamma rays, the positron electrons are split. You can see that there is a curvature in the opposite direction of what was expected. and by this the positrons, antiparticles of electrons were detected. So he was offered a second Nobel Prize, and so basically there were one, two, and three Nobel Prizes offered with this in the chain of this cloud chamber. VTR, CTR Wilson. CTR is Wilson itself got a Nobel Prize in for proving the Compton effect, very famous Compton effect, and he said Nobel Prize with Compton in 1927. These were two other scientists which got the Nobel Prize. So it is very celebrated discovery, invention of this chamber. It was at this time it is true that we have a more far better instruments to detect the particles, but at that time it was nothing less than a revolution. It was just splendid. You can if you see the tracks now also, as you will see in this presentation, you will see the tracks live in the video, and you will be fascinated too. It just looks very beautiful. It looks very calming. So this was the very celebrated discovery. These were the scientists behind upgradation. And after cloud chamber, it came bubble chamber. Bubble chamber was also the inventor of that bubble chamber was also given the Nobel Prize. So yes, so it has a very vast impact on the humankind's and nuclear physics field of nuclear physics. So now, can anyone see me? Tell me, am I audible or clearly I'm going? Anyone give me response?
Yes, yes.
Yes, yes.
You
Okay, thank you very much. So, is my speed okay with all of you, or is bit fast? Can you can also
yes,
tell me
yes.
that?
Okay,
Yes.
okay.
Okay, thank you. Now we shall discuss about the working of the diffusion cloud chamber. Now the cloud chamber that Wilson created or invented was a cloud chamber using water as a vapor. And this was something different upgradation, which was made by Alexander Langstroth. He modified the cloud chamber and in a certain way, and he created a box type shape, and it was very efficient. It is easy to carry. You can carry it anywhere, and you can. In here, he used alcohol. He used alcohol as a paper. Now, using alcohol, why alcohol is used, a key part here, the which would be cleared very soon. So instead of first in Wilson cloud chamber, there is a supersaturated form of water vapor. When the volume pull down the piston, the volume expands, and then the pressure falls, and the water droplets that waters that are means water is present, it condense on that molecule, the tracks, ions, and you see the tracks of the particle. But here there is an use of alcohol. Now what happens when the charged particles passes through these molecules? Suppose you have a supersaturated alcohol vapor, which is just on the verge of condensation. Just on the verge of condensation means when there is any disturbance created in this medium, there will be condensation happening. Now, how it will happen? I will explain here. Keeping that supersaturated form has been achieved, when the charged particles collide with these gaseous molecules, they are highly energetic, and they lead to ionization of that atom. Upon ionization, you have positively charged ions, which which are nothing but the site of condensation. Now surround now the if the supposing that charged particles collides with an atom or gaseous molecule, leading to ionization. That ionization created positively charged ions. That electron which has been removed from that molecule or atom is captured by the surrounding alcohol molecules or any gaseous atom, and they become negatively charged. So now there is a pair of charge positively charged ions and negatively charged ions in that region where there is a passing of the charged particles. So these are nothing but the site of condensation. The surrounding molecules of alcohol condense on ions as they are polar and having dipole interactions. They condense on these molecule ions, and we see uh, mist-like tracks, white mist-like tracks which are nothing but the droplets which have been condensed. The vapor has been condensed to water, and we see that there is the droplets, thick droplets tracks, white tracks. It looks like a mist. When there is an aeroplane passing, you see where sometimes when there is in sky there is an aeroplane going, and you see the track behind that aeroplane. That is nothing but the same principle that is happening here. The aeroplane is passing in the sky, and you see the track of the and by that you say that, oh, the aeroplane has been uh, going aeroplane was there and was going from here. So that is happening here, and there are aeroplanes, and here there are tracks, the tracks of the particles of the nuclear physics, the particles. So on condensation, mist like tracks are seen, and they are called, we name as the tracks. these are these are nothing but the footprints of the particles. It depends on the energy, mass, and other parameters. For different particles, there are tracks are different. Some are thin, some are thick, some of them are long, short, etc. So based on the size of the particles and thickness of the particles, we determine that this is this particle and that is this particle. So by that, scientists used to discover many more particles, and this was this became the first particle detector. As no one was aware that how it looks. At the first, Wilson was very confused. That what is this thing happening? He was not aware. But he realized that Henry Becquerel and Marie Curie itself told that there is. So Henry Becquerel and Marie Curie told that atom is not stable. It disintegrates into different type of particles. So uh, by that he realized that this is something else, and this is the what particles, there is a disintegration of the atom, and we are having the particles. Checking that, he used a source, any source he put in the chamber, and he found a similar tracks of the what he was used to observe earlier. So he realized that this is nothing but the tracks of the elementary particles, of the nuclear particles, which are we are seeing. And this was there was a dramatic shift from having a atmosphere to having a detector who is detecting the particles. So this was it, and it was very efficient. So now I will give you idea that how do we achieve super saturation. In the earlier slide, I have told you that we are having a super saturated vapor. Here, this is a super saturated vapor, alcohol vapor. And now I will tell you about how we achieve that supersaturated vapor. So firstly, it is by means of temperature gradient. Now there will be entry of something very crucial in this experiment, in the diffusion cloud chamber, something which is very crucial, and that is dry ice. Everyone have seen dry ice. It is like solid CO2. There are pictures in this PPT. You will see that in later also. And the dry ice CO2, which has a temperature minus 78 degrees Celsius. So that is kept at the bottom of this chamber. So and the top there is isopropyl alcohol soaked in the felt. I will clear all these terms like how it is soaked and where is the bottom, what is the chamber, how it looks like in coming slides. It will be very clear. But I thought that I should discuss first how it works, what are the principles, and then I will discuss how I achieved that. So here we will accept that at there is a dry ice. Imagine there is one chamber. There is one chamber like that. This is a chamber. Here I have put dry ice, slabs of dry ice. Here I put slabs of dry ice, and here I have a felt. At the top, I have a felt, and I have soaked alcohol here. You have soaked alcohol here. Now what happens Due to very low temperature inside the chamber, the pressure decreases. Now, how the low temperature is achieved? As you can see that there is a minus 78 degrees Celsius here, and here 20 degrees Celsius. So obviously, if we calculate the difference between these two top and bottom, the temperature gradient is very high. It is like there is a very low temperature in this in the cloud chamber. The greater we go downward, uh, downwards, the temperature decreases, and we see it, and we have a very low temperature near the bottom. So there is very low inside the temperature, and as you know, PV is equal to nRT. As temperature decreases, pressure decreases, and the alcohol vaporizes down by falling from high temperature region to low temperature region. As I discussed, alcohol starts falling down from high temperature region to low temperature region. Now, near the bottom, temperature is approximately minus 30 or minus 20 degrees Celsius. If you take a difference, and also if we take that this is a metal plate, an amount of conduction, and considering all the heat loss from surrounding and all these things, temperature loss. So we consider that okay, there in this region at the near the bottom, the cloud chambers, there is minus 30 to 20 degrees Celsius. So more the alcohol, as I told you, come near the bottom, more likely it become to condense. Now, as you know, there is a vapor, and you cool it more and more and more. Then it will start at some point. It will turn into liquid by condensation. Then you cool more, and then it will start to become ice, solid. It will start to freeze. So similar things is happening here. There is a temperature high here. The temperature is decreasing, and it is very cold here. At this temperature, the alcohol vapor, the vapor that is present, is very likely to get condensed. When there is any disturbance uh, uh, created in this region, the we disturbance created in the region, there is a condensation process going on. So now, what are the disturbances? Of course, the disturbances are like the particles that we have discussed before, and that is what the key part of this cloud chamber, working of the cloud chamber. We are witnessing the disturbances only that is created by these particles, and these particles and hence are detected with their footprints of the specific impressions. Now the thing is, there is one of the disadvantage of these particles, cloud chamber, is that they they don't. There is not a vast region. The active region of this is not a big one. It is limited to certain height only. It is limited to certain height. Like, we do not have a particle detector at the top or bottom. Of course, I told that there is no condensation here as there is a temperature is high, but there is no particle detection here. So it is limited by this small region at the near the bottom, and that is one of the disadvantage of this chamber. And Wilson cloud chamber, when you expand the whole atmosphere that is there, whole the volume is there is converts into supersaturated vapor, and condensation is at large region. There is a equal decrease in pressure at all regions, decrease in temperature. So this is something disadvantage, but we cannot say the disadvantage. It can be increased by reducing the dimension of height. It depends on the height of the chamber, of course, area and amount of dry ice or cooling you are providing, amount of alcohol you soaked in the chamber, and that matters a lot. So this is one. It likely becomes condensation to decrease the temperature more. Okay. So we have supersaturated alcohol at the bottom, ready to condense all the disturbances. So this is nothing but the active region where the particles are detected. So I hope you all have cleared that how supersaturation is achieved. It is nothing but the temperature gradient, as I talked. Below is solid ice minus 78, and this is 25. Pressure decreases, temperature decreases, and then condensation take place, and then boom, we get the particles. And this is the stuff going. This is the working of the cloud chamber. I have discussed the working of the cloud chamber. Now I will tell you how I made the and my particle chamber, and what were the necessities I kept before designing or making of the cloud chamber apparatus. In any kind of experiment, I consider, for me, the most crucial part is the apparatus, because if you take or use some wrong apparatus or some of low configuration of or some of like wrong things in your experiment, then you might not get results. Even if you do procedure accurately, you might not get the results. So the very crucial part is, after aim, is that you decide what apparatus specifically you will use, because your target is the results that you want to obtain. So I will emphasize on what type of apparatus I used. So, setting up my experiment. So this is my aim. I will proceed like any college journal or high school journal that we have. We have aim, we have procedure. I want you to make your own chamber. So you make your own chamber and see that live. So you can see that how I did, and it is your choice if you want to make it like me, or you want to modify something on your ideas or something like that. So I will go by that only. So you can mimic it and have your own cloud chamber. So first of all, we want the diffusion cloud chamber. We want to ionize. We want to detect the ionizing radiation. That is our aim. Ionizing radiation could be any particle or something like that. Now this is the apparatus that I used. First of all, I used a chamber of size that I decided. That is the first. I mean, there is something, you can take any size of the particle, of the chamber. Sorry, you can take any size of the chamber based on how big you want and how efficient. Based on that, you need modification in these things. But I selected an optimum size of a rectangular chamber. The chamber was this. This is the chamber I use. It was of acrylic. Now, reason for using acrylic is simple, that it is more durable than glass, and it is not that heavy that as glass, and it is more durable and could be carried. And the sole purpose was just to make it more efficient and durable to carry at anywhere and make it comfortable. So I used acrylic fiber. Of course, it was costly, but it is okay. Now, this was the chamber. You see, this is not that is it fixed by sellotape. Please don't misjudge it. It is attested by some glue or something like that, which is very efficient, which is tight. Now you have to remove this all these papers to have a class. Now, making of these holes. You see, there are holes here. I decided to make these holes. I told the maker of this chamber that I want holes at this distance and at this all corners. So this was the planned thing, that I want holes. The I use this hole to tie the soak sponge sheet at the lead part. Here at the bottom, as I want to tie the uh, alcohol, the sponge sheet, I used I used holes by penetrating ribbons in this and then tying it up here. You will see in the figures that I will show you for in ahead. So this was the dry ice. This type of slabs I have used, which I have kept at the bottom of the chamber. This is the dry ice, and this is the isopropyl alcohol. Now you can use any alcohol like methanol, ethanol, isopropyl alcohol. The main importance of using alcohol is like its ionization potential, how much energy it needs to get ionized. Like for alcohol, it is 10.10 eV. This alcohol, isopropyl alcohol, its freezing point. That is also very important, because you are keeping minus 78 degrees Celsius beneath the chamber, at the bottom of the chamber. You don't want any medium or any liquid to get freezed at that, in the chamber. It will If it will freeze, then there is no vapor, and there will be not any detection. So this alcohol has minus 89 degrees Celsius freezing point. freezing point was minus 89 degrees Celsius. So there were no chances of getting it freeze in the chamber. And we have a very good condensed vapor, alcohol vapor in the chamber. So, and here you can, if you can zoom out, you can see it is a 99.0% concentration. Concentration is also most important thing here, and the concentration here is 99.0. And why it is important? Because you want to get a good saturation. You want to get a dense saturation. You want maximum alcohol vapor in the chamber, so that it gets condensed easily on some positive ions surrounding it. And as per the literature, it is told that it should be more than 90% concentration. Concentration should be more than 90%. And I have used this 99.0% pure alcohol, isopropyl alcohol. Now I will show you the thermocol base that I used for holding this chamber. This was the thermocol section that I carved out from the thermocol sheets. I made this on my own, and I attested these all corners. You see there is a, these are not of same size. This has to be tight. So I keep that this slide more this of more length and this of short. And similarly at all ends I have connected like this. So maximum packing is obtained, and I have to put here dry ice here. I'll put here slabs of dry ice. I will keep the slabs here, and this is the chamber. And sorry, this is the sheet, thermocol sheet, the section that I will use. Next, this is how it is kept. You can see here the box is kept based on its dimension. This area is calculated, and the seats were cutted down, and it was cut such that it is best fitted here. So this chamber is kept here, and it is stable. It remains fixed. And next, I attached LED lights at the near the active region. You can see here I have just given supply. I have extended this wire, and it at the at the top I have AC to DC converter. So I'm using AC energy, which converts which AC energy, and that is here I have 12-volt DC converter, and that powers DC to gives DC to this LED, and this is lighted. So this is attested near the bottom region of the chamber. As our region of interest, as I discussed earlier, is especially at this bottom region. You will see in the videos also, we have a bottom region very efficient for detecting the particles. This is the region where the particles are detected. So I kept LED at downside. So this is how it looks. As I told you, I connected, this is the felt, if you can see. This is the felt in which I will soak the alcohol, this sponge sheet. And this is tied with using this thread from the holes that I discussed earlier. You know, I told that I have made holes here, so I can tie this sheet. There are this, and there are two strings used to tie this felt. They were also glued, of course. Due to weight of the alcohol, it may fall down, but I have, for safety, I have used thread and also glued it with a glue gun. So this is the total setup of the alcohol soaked with a sponge and tied on the lid of the chamber. Here, AC to DC converter, I have attached it afterwards, and I have, it is at Ahmedabad. I have note. I don't have any figures or images particularly of that chamber, total chamber. You will see in the proceeding slides my whole setup, and here I have connected as LED. And this is with this is the complete setup ready to roll. And this is the, I have just, it is just for design. You can do any colors and do also, so anything, but I kept it black. And also I have used cello tapes here. I have make sure that I have sellotaped it here at all corners, so there is no leakage or any kind of air going inside and decreasing the efficiency or cooling of dry ice to giving cooling to this chamber. and this was done. And you can see here, this is the bottom. This all one, two, three, four. These five faces of this cube, rectangular cuboid, is uh, is uh, is of glass, but the bottom is a metal. Is I want a good conduction of cold, dry ice, so that there is a maximum less temperature here. So what I did, I used metal sheet here, aluminum metal sheet at the bottom surface, as a bottom surface, and I attested sellotapes here, dark sellotapes, as to avoid reflection from the metals slide and to interfere with the tracks. My tracks might not get. So I want this region, bottom region, dark also and of metal also. So I use that. Now the procedure. How I performed the experiment depends on the procedure. How I use the procedure and what procedure I follows. After what step I should do, other step, which step I should go on. So first step is to open the chamber and tie the sponge on the lead surface such that the sponge remains inside the chamber when it closed. So as I said earlier, I have to tie a lead, a sponge sheet on the lead. I have to tie it first and do that, and close the chamber tight, making sealing perfect. Now, as the lead, after soaking the isopropyl alcohol in good amount, closing the chamber, you have to seal it such that outer air does not go inside the chamber. As air has a low freezing, high freezing, 0 degree air freezes, and therefore it may happen that you will get clouds, structures, or some direct condensation in of air in the chamber. So you don't want maximum. You don't want outer air to go inside the chamber. It will decrease the efficiency of detecting the particles or the supersaturated alcohol vapor. So you don't want air inside. So what you will do? You will do sealing. Sealing from the sides, sealing from the top. You holes here, so obviously there will be air going inside. But I have sealed it with sellotapes so that air does not go inside. Cello, I tested sellotapes at all the corners of the chambers and all this thing. Black chamber, keep your hands and eyes away from isopropyl alcohol while soaking. Isopropyl alcohol is not good for eyes. It is good for experiment indeed, but not good for eyes. So you better keep safe your hands and eyes from it. Wear experimental glasses to protect your eyes. So these are the protective measures you should take before doing the experiments. Isopropyl alcohol is used. Therefore, now with care, put the dry ice in the thermocol section using safety gloves. Handling dry ice also requires safety gloves, and you need to put the dry ice now in the thermocol section. After putting the dry ice in the thermocol section, put the chamber upon the dry ice. Now I have kept the dry ice, and now I will put the chamber inside that thermocol section I have shown before, such that it is fixed and it is not shaking. Cover the edges with sellotape as I discussed, such that cooling from dry ice is not wasted. Do proper sealing. Now switch on the LED lights using power supply AC/DC converter, as I told you. Wait for 15 to 20 minutes for seeing one of the most celebrated beauty of nature. Now you have to wait for some minutes. You will start seeing the particles suddenly. You'll see and you will be very excited by seeing the videos. I'm sure. Now there are different kind of tracks like short and thick, long and thin, V transformation, curvy shape tracks. This is the procedure we have to do. Very simple it is, and it is also very exciting for me. And now I will go on to result and observations that we obtained. This is the result. The first track is of alpha particles. You can see these alpha particles tracks. These are the alpha particles. What I have did here is I have images from my experiment, and I have images from the literature. This is the proven thing that this type of tracks are nothing but alpha particle tracks. I have also tested references. Now, this alpha particle tracks are thick and short. approximate 5 centimeter. Heavy mass, they have heavy mass. Now they have heavy mass, they they get hardly deflects from its path. They travel straight. It does not get deflects by colliding. It passes straight and almost ionizes all the molecules atoms coming in front of him. Whatever atoms it will come, it will ionize it, as there is a maximum cross section of interaction between these molecules and alpha particle due to its large size, and therefore we have a thick and short track. As they have maximum collisions and ionization, it it loses its energy very suddenly, and we have a short track. It loses its energy as, as there are maximum collisions, and the sources which are a natural radiation, radon 222 gas from surrounding radioactive decay. This radon 222 is a natural isotope which is present in the earth crust. It is very common in all the buildings or in all the construction sites. You will find radon 222 isotopes in earth crust, and that comes, and that is why we have alpha particle tracks. We don't have alpha particle tracks coming from cosmic, as they will, before coming down, they will easily get interacted, and you not. But these alpha particles are nothing but some, due to some of these isotopes, radon 222 case, which you find in your building or in your house or something like that. There is there isotope is there, and you see that, I see that radon alpha particle tracks. So you see this. This is a alpha particle. Some of the tracks are large also, and that is due to, I have also obtained some large alpha particle tracks. It may happen that some of the alpha particles have high energy, and therefore it travels more than what the short one do. This is very short and this is very long. It is alpha particle indeed, due to its thickness and all. You have in literature also, it is said that some particles may be long and some particles may be short. Here, so this is the video which I would like to show you. Let us go on it. What I want to do. Now we shall go to this link. This is the video of my chamber. You can see here. Now I will play this. Is visible? Video is visible to everyone? Can anyone respond it?
Yes, yes.
You see there are tracks. Now there will be alpha party. You see there are this also tracks, but I will discuss it later. The video is solely for alpha particles. You can see different tracks also other than alpha, but photo electrons and all. See this long particle, alpha particle. This is straight and thick and long, a short. You see other two particles also, alpha particles. Now you don't have radon 222 everywhere, so you see the alpha particle tracks are here, some less rare. See these two tracks. Have you seen that? See these two tracks, alpha particles. You have short and thick. This was the very first time I used the chamber. I have me and Kishan. We were both here doing this experiment at our home, and this was very fascinating at that time. This was the first time we detected the particles. So yes, also this was the alpha particles. That this was the first particle tracks I explained here, and we detected. Second were the photoelectrons. Now you all know the photoelectric effect, which is by photons or gamma rays. They knock off the electrons from the metal plate or something like that, and we have electrons of low energy. So these are the electrons, photoelectrons. These are photoelectrons, and they are of low energy, set free by uh, high energy gamma rays or photons. And the sources are photoelectric effect, beta emitters, ion transformation, all that. These tracks are curly tracks. Photoelectron tracks are bit curly as they are of less mass and of low energy. They don't have a straight and long track, but due to low energy, they easily get hello. They easily get deflected, and we have curly tracks. Now I have pointed out here some of the curly tracks. See this one. This is a bit curly. This is also a bit curly, and this is also a curly track. So I also detected the photoelectrons. These were the in these were a plenty in plenty amount, as I used here LED source that the enough photons are there, so enough photoelectrons should be there. So these were the photoelectrons that I detected, and for that there is a video. See the short, you will see the this is basically beta emitter. This I have obtained from the college, St. Xavier's College. I have obtained this. They gave me strontium 90 beta emitter. Beta, they're nothing but electrons. But we are also detecting here curly short tracks, photoelectrons, which are also emitted by beta emitters. See this curly, the short disintegrations. See this curly this short tracks. This here. You can see long tracks also. They are something. They are highly energetic electrons. They also get bent, but they are energetic than photoelectrons. You see long tracks and these short disintegrations. These are the particles. This sort. Another thing is like, see, this is an alpha particle. How beautiful it looks. And you see the cloud, the vapor that is at the verge of condensation is at very near to the bottom surface, as I discussed. So these are, and there is this is the LED light which I attested as I discussed, and this the tracks. This is a cloud. This is a beta emitter. The problem is that beta emitter should be kept facing this side, but it is upside, so we are not detecting much particles. Otherwise, we have seen much nicer tracks of beta particles. And as the chamber is at Ahmedabad, I'm not able to go there and take that due to some certain restriction from house and due to corona and that all things. And from 8 months, he's lonely there in my room. These are the photoelectrons, short curly tracks. Now, this is something very rare. V-shaped double alpha particle tracks. This is these tracks similar to this type of tracks. I obtained this V-shaped double alpha particle tracks. Now, from where it comes, I will explain that. So we have a radon 222, which is another isotopes other than radon 222, root 220, sorry, radon 220. And in the cloud chamber, it gives off two alpha particle tracks within very short time. It decays into polonium 216, and it suddenly decays to late 212. So you have a two in the decay change. This is nothing but a thorium series. We have four series, and one of them is a thorium series. And that decay chain, we have a radon 222 decaying to polonium 216, and suddenly decaying to 212. And both decays, you can see 220 to 216, there is a difference of 4. So for alpha particle, it is helium nucleus with 4 He2. So obviously, we are seeing alpha particle decays here, and this is alpha particle decaying suddenly into one and two. Here it is decaying, and then suddenly the second decay. So we get a V-shaped alpha particle tracks, thick V shape, and similar to that, I am obtaining here. You can see here I am obtaining here also V-shaped double alpha particle tracks. And secondly, I have obtained beta particles, which are very common. Beta particles in electron. Now, the thing is, you cannot differentiate between positrons and electrons. Positron, which I have told here, is the beta particles and electrons. They are only can be distinguished if you have a magnetic field. They can give a band a particle in a certain way. As we have discussed, that Carl Anderson did an experiment in which he detected positron by using a magnetic field and noticing the deviation in different direction. So this could be electron, or this could be beta electron, but they are both same mass. Just the charge is difference. They are antiparticles of each other. They form as they have enough energy to travel long, but they easily get bent also. So we have this in literature. We have these beta particles, curly tracks. You can see here, long and curly track. It get bends, and we have this type of tracks. Now here you see these tracks I have obtained in my chamber. It is a long and very it bends here. See, it is a long and it bends here. So this is the possibly a strong possibility that this is a beta or electron particles. Here you can also see it is a straight. It is straight. It does not get bent. It may happen that this is high energetic electron. It is straight and it goes off and it does not bend. So if you have strong beta emitter source which have high energetic electrons emitting, you can observe this type of long tracks also. You see, this is a long track and straight track. This is also from literature, and similar tracks I also obtained here. This is also one of them, curly tracks and these all things. So these are the beta particles electrons which we get in the cloud chamber. Now, sources of that could be like any, could be a gamma ray disintegration. Gamma rays converts positron into electron, and by annihilation, and also from you can have a cosmic particles also, electrons, beta particles, and they get bent, and you detect that these curly tracks. We will see the video of it. This is the video for beta particles and electrons. See, they- they're getting see, they're getting curved and long, and see this this getting bent. This type of this track, these small tracks. This is also we did in VP Science College. Me and Kishan, we went there and shown the experiment there. This is the long tracks event. See this one, all this. See, you can see long and bent tracks. See this. This was a basically a different particle which I will discuss. Skip bending tracks. Now we have different tracks that are protons, and protons, as per the literature, are thinner than alpha particles, but are thicker than electrons, as their mass is more than electrons, and we have a long and slight thick tracks of protons. Now, protons are cosmic particles from like a sun or something like that. We get the protons or any different uh, hydrogen nuclei or any something disintegration. We will get protons, and these are the tracks of proton from literature. And similar tracks I obtained in my chamber. See this, there is it is covering almost the entire thickness of the chamber. See this and this. It is thick and a bit long than alpha particle. So these are the tracks of proton that I obtained. Now I also the sources are cosmic. These are the video. Here also you can see some electrons or beta particles. See, photoelectrons are in plenty. You see this curly track here. Have you seen that? That curled. This integration D. This curly, this curls. And this is some slight curl and tracks. See these tracks. Here you can see. You will notice one straight track here. I missed that. Okay, let me show you in that different video. This one. If you remember, I have told you that there is a long see this long track. That is a proton. See how long it is. It covers almost entire range of this chamber. So size selecting the size of the chamber also matters here. If you want to detect long particles before it gets, if the size of chamber is low, then you cannot say that this is the beta or alpha or something like that. If the length is the problem. Many alpha particle tracks. See this. This is something else I will show. And lastly, the very rare I detected was the rare muon track. As per the literature, it is like this. And here I have detected straight thin and how energetic rare muon. It is very thin and it is very straight than the electrons or beta particles. It is almost very straight and very thin. And this is from literature, and this is from what I obtained in the cloud chamber. And the sources of them is cosmic, of course, and how why it comes is a relativity, and due to relativity it works. If you have studied that due to as they are very low, as they travel nearly at the speed of light, the time gets dilated for them, so they can easily, after creating from the atmosphere, having approximately, I don't remember exactly, but it is like 2.6 and 10 raised to minus 6 micro 10 raised to minus 6 second is the half life of the muon is that. But due to its very high speed, near the speed of light, it easily gets travel down to earth at the surface, and can easily penetrate 30 to 20 meters beyond the earth, because it is very rare to interact. Now I have also obtained that muon track here. It is long, straight, and highly energetic. So, by this, I would like to conclude my session. So, thank you everyone for joining me today. I have explained you about the history of how it invented, how it works, what I did, what was the procedure, what was the results obtained. Now, I hope you will also do that same things, or even modify it slightly, and build your own cloud chamber. You can see this is this is this is DC to DC converter I talked about, and this LED. This is a photo of VP Science College where we enjoyed a lot demonstrating the cloud chamber. This is the box, and in which I kept a dry ice. Me and Kishan, we went there, and we made a great friends too. And these are the photos which would be with me for lifetime, I guess. I have a great motivator guide, and Dr. Tushar Pandya, who unfortunately passed away recently, and that was a great loss to Xavier's family too. And he after the fun part is that after I did experiments, and soon in the this you can see this is our experiment lab. The dark room is required indeed to see the particles, and we all the my colleagues have gathered here. This is Jahan, and Kishan is this this is Bhavya, and all these are here. And Jai has got some weird eyes. That is photography, of course. Now, and the Tushar Pandya sir used to call me after this experiment JJ Thompson, which was very funny for me. But he was very friendly to me, and best motivator I had in my life. And you see, all other professors are also there, which were very fascinated by seeing these particles. Here I have references. This is my email ID. You can ask me any questions here also, and also in this talk if you want to. I also want to thank the management team, Michelle, Jahan, Uttam Bhai, and Dilip Bhai for making this successful, and to manage this all streaming and all these things. I want to thank Kishan and Jahan personally, because Kishan has helped me a lot with this chamber and carrying it, and being with me in this chamber, and in college, and VP Science presentation, and also Jahan for giving me the transport facilities at Ahmedabad, because I don't have any bike and all the stuff there. So he provided me the vehicles and that stuff to get the dry ice and all this thing. And so it was a great support from my colleagues too, which made this all possible. And here I have that is the references. Now I'm open to questions if you have.
मेरी आवाज आ रही है? आ रही है ना? यूट्यूब में जो व्यूअर्स देख रहे हैं, अगर उनको कोई क्वेश्चंस पूछने हो तो वो
हाँ
गूगल
तो
मीट पर पूछ सकते हैं.
हाँ तो चैट बॉक्स में से कोई भी रीड आउट करके यहाँ पे पूछ सकते हैं.
Yes, yes.
First of all, you give me the feedback, like how if you liked and what it looked like, and because it helps me to upgrade myself. It is very necessary.
जय, अगर मेरी बात करूँ तो मैंने ऐसा फुटेज अभी तक कभी नहीं देखा था, और इतना अच्छा एक्सपेरिमेंट पार्टिकल्स को नेकेड आई से देखना पॉसिबल है ये मुझे पता भी नहीं था, क्योंकि मैं केमिस्ट्री का स्टूडेंट हूँ, इसीलिए मुझे तो बहुत ही अमेजिंग लगा। और
आई एम
ऐसा भी
ग्लैड
फील
दैट
हो रहा है कि शायद फिजिक्स पढ़ना चाहिए था मुझे यूनिवर्सिटी डिग्री में।
nothing is late. Nothing is late. You can do it anytime. Thank you very much, Uttam bhai.
और व्यूअर्स में से किसी को फीडबैक देना हो तो दे सकते हैं।
और क्वेश्चंस भी जिसको पूछने हो, आई विल ट्राई माय बेस्ट टू आंसर। अगर नहीं कर पाया तो मैं मेल करके आपको आंसर तो भेजूंगा ही, दैट इज फॉर श्योर। बट यू कैन आस्क टू एनी क्वेश्चंस।
अगर आंसर नहीं भी कर सकते तो हम दूसरों की क्यूरियोसिटी तो बढ़ा ही सकते हैं।
हाँ, दैट इज व्हाट साइंस कम्युनिकेटर डज। we are all communicators, we are all science spreaders.
मेरे भी 2 क्वेश्चन है, मैंने भी लिखे रखा है।
Okay, okay. So any questions? We'll wait for 5 minutes, 5 to 10 minutes.
ओके।
Are everyone there?
હેલો જયભાઈ,
हाँ बोलो।
આ તમે જે સોલિડ જે CO2 યુઝ કર્યો એની જગ્યાએ
हाँ,
તમે બીજું કઈ યુઝ ના કરી શકો આમાં જે
મારે
ટેમ્પરેચર માઇનસમાં લઈ જવા માટે?
બીજું તમે યુઝ કરી શકો, લિક્વિડ નાઇટ્રોજન યુઝ કરી શકો.
હું એ જ વિચારતો હતો કે લિક્વિડ નાઇટ્રોજન યુઝ કરી શકાય કે નહીં.
કરી શકાય, એમાં કોઈ
હા.
પ્રોબ્લેમ નથી, કારણ કે લિક્વિડ નાઇટ્રોજન, પણ હવે લિક્વિડ નાઇટ્રોજનનું ટેમ્પરેચર કેટલું લો છે, -11411 એના કરતા ડિગ્રી નીચે છે. તો હવે એવું આલ્કોહોલ બી તમારે યુઝ કરવું પડશે ને, જે ફ્રીઝ ની થઈ જાય ચેમ્બરમાં.
પણ એમ નહીં કે એ તો ગેસ જ છે ને, તો આપણને ટ્રેલ ના મળી જાય એમાં એમાં પછી ગેસ આલ્કોહોલની જરૂર શું પડે પછી એમ?
એમને થોડી કોઈ આલ્કોહોલની જરૂર એટલે પડે કે આપણે કન્ડેન્સેશન કરાવવું છે. ડાયપોલ પોલાર મોલિક્યુલ્સ એટ્રેક્શન કન્ડેન્સેશન થાય અને એનું આપણને ટ્રેલ્સ મળે. વોટરમાં મળે, નો ડાઉટ, વોટર ઇઝ ઓલ્સો પોલાર મોલિક્યુલ, બટ વોટર સ્ટેબલ એટ -89 ડિગ્રી, -30 ડિગ્રી સેલ્સિયસ. એ ફ્રીઝ નહીં થઈ જાય 0 ડિગ્રી પર.
0
એને
ડિગ્રી પર
ક્લાઉડ્સ
તો
થોડી મળે. હા, એના
હા
ક્લાઉડ્સ નહીં મળે ને આપણને. આપણને
હા
ક્લાઉડ્સ જોઈએ છે, તો આપણને એવું કંઈક લિક્વિડ વાપરવું પડે જે ફ્રીઝ નહીં થઈ જાય. એને વેપર ફોર્મમાં રાખવાનું છે આપણે, અને થોડુંક બી ડિસ્ટર્બન્સ થાય તો કન્ડેન્સ થઈ જાય, પણ લિક્વિડમાં કન્વર્ટ થતું એવું રાખવાનું છે. આપણે સોલિડમાં કન્વર્ટ થઈ જાય એવું નથી રાખવું. હવે આલ્કોહોલ યુઝ કરવાનો મતલબ અહીંયા એ જ છે કે અહીંયા આલ્કોહોલના લીધે એ આલ્કોહોલ ને બીજું તું લિક્વિડ નાઇટ્રોજન યુઝ કરે તો આ સ્ટેબલ થોડી રહેવાનું છે. હા, રાખી શકાય એવું નથી, બટ પછી તારે આ ચેમ્બર નીચેનું કાઢ નાખવું પડે, મેટલ પ્લેટ કાઢ નાખવી પડે, અને મેટલ પ્લેટને અહીંયા થર્મોકોલમાં એના 2 પાંખડા કાઢીને આમ ઘુસાડીને બેહાડવી પડે, અને નીચે લિક્વિડ નાઇટ્રોજન ભરવું પડે, અને અહીંયા આલ્કોહોલ બીજું યુઝ કરવું પડે આ ચેમ્બરને
બરોબર.
સ્ટેબલ રાખવા માટે. વાત સમજ. હવે લિક્વિડ ઉપર આ ચેમ્બર તરે તો હલિયા નહીં કરે, અને સીલિંગ કેવી રીતના પ્રોપર મળે, અને કોઈ બી હાથ લગાડે તો આમ તેમ નીચે ઉપર નીચે થાય. એટલે સોલિડ
હા
CO2 યુઝ કરવાનો મતલબ એ જ હતો કે વી વોન્ટ અ ફિક્સચર, we want a stability, we want optimization to detect the particles and have a good atmosphere by using isopropyl alcohol, which is easily available. Another than liquid nitrogen ને યુઝ, અને એને લિક્વિડ નાઇટ્રોજન ને સ્ટોર કરવાનું, એને યુઝ કરવાનું બી બહુ અઘરું છે ડ્રાય આઈસ કરતા.
અને હું બીજું શું વિચારતો હતો કે આમાં તમે કોઈ પણ જે પાર્ટિકલ છે એ ચેમ્બરમાં જ્યારે એન્ટર થાય તો મતલબ અંદર OH મોલિક્યુલ્સ તો હોવાના જ અંદર, કારણ કે અંદર આલ્કોહોલ તમે નાખ્યો એટલા માટે. તો OH અને તો મતલબ બંને અલગ અલગ નથી, કે મતલબ કે સાથે સાથે જો ઇલેક્ટ્રોનની એક પેડ મળવી જોઈએ ને સાથે સાથે આપણને, કારણ કે ઇલેક્ટ્રોન રિલીઝ થતો હશે કદાચ અંદર.
તો એ મેં તમને કીધું ને, ઇલેક્ટ્રોન રિલીઝ થાય એટલે પોઝિટિવ આયન બને. આ
એમ
ખબર
નહીં,
પડી
હું
પોઝિટિવ
શું
આયન
કહું છું,
બને
જાણે
છે.
કે જો અ, ગમે ગમે તે કોઈ પણ તમે પાર્ટિકલ લો, જાણે કે પ્રોટોન પ્રોટોન એન્ટર થયો છે અંદર પાર્ટિકલ ચેમ્બરમાં, તો મતલબ સાથે સાથે OH મોલિક્યુલ, એ OH મોલિક્યુલ છે એને પણ ડિસઇન્ટિગ્રેટ કરી નાખે ને, તો સાથે સાથે એક મતલબ ઇલેક્ટ્રોન પણ છૂટો થતો હશે સાથે એમ, તો
હા, તો
એની પણ સાથે બીજી એક ટ્રેલ મળવી જોઈએ ને.
એટલે એક OH મળે, OH માઇનસ મળે ને ઇલેક્ટ્રોન મળે એમ.
હા, તો સાથે સાથે એની પણ એક ઇલેક્ટ્રોનની પણ ટ્રેલ મળવી જોઈએ ને સાથે.
હા, તો
Can I
મળતી
answer
જ
this
હોય ને.
question?
યસ યસ.
देखो यस, जो OH मॉलिक्यूल की बात कर रहे हैं वहाँ पे ऑक्सीजन और हाइड्रोजन के बीच में कोवेलेंट बॉन्ड है, लेकिन जो जो प्रोटॉन चैम्बर में एंटर कर रहा है ना, वो ऑक्सीजन के ऊपर के जो लोन पेयर वाले इलेक्ट्रॉन्स है उसके साथ सिर्फ हाइड्रोजन बॉन्ड बनाएगा। वो वीक बॉन्ड है, कोवेलेंट बॉन्ड ज्यादा स्ट्रांग है। तो ये हाइड्रोजन बॉन्ड प्रोटॉन का जो है नया बन रहा है, वो कोवेलेंट बॉन्ड को, यानी ऑक्सीजन और हाइड्रोजन के बीच के कोवेलेंट बॉन्ड को ब्रेक नहीं कर पाएगा। शायद ये एक रीजन हो सकता है कि जो आप एक्स्ट्रा एक ट्रैक एक्सपेक्ट कर रहे थे वो नहीं मिल रहा है।
બેઝિકલી ઇલેક્ટ્રોન તો છૂટો પડે જ, એક ઇલેક્ટ્રોન છૂટો પડે અને બીજા બી થતા હશે બેઝડ ઓન ધ કોલિઝન્સ એન્ડ ઓલ ધીસ સ્ટફ. એ ઇલેક્ટ્રોન કેપ્ચર બી થતો હશે અને બીજો જે આયન બને તે નેગેટિવ ચાર્જ બને, જેમાંથી નીકળો એ પોઝિટિવ આયન બને. તો આપણને બેઝિકલી પેર ઓફ આયન્સ મળે છે અહીંયા, પોઝિટિવલી ચાર્જ નેગેટિવ ચાર્જ બંને એટ્રેક્ટિવ છે. આલ્કોહોલ બીજા આલ્કોહોલ મોલેક્યુલ જે ન્યુટ્રલ હોય એની પર કન્ડેન્સ થઈ જાય. એન્ડ અહીંયા મને એવું લાગે કે થોડું કેમિસ્ટ્રી ભણવું જોઈએ, બટ આઈ વિલ ગેટ બેક ટુ યુ ઇફ ઇટ ઇઝ નોટ સેટિસ્ફેક્ટરી ટુ યુ, બટ આઈ વિલ ગીવ અ પ્રોપર રીઝન. એની અધર ક્વેશ્ચન્સ?
मेरे 3 क्वेश्चन है।
यस.
एक तो ये कि आपने IPA यूज किया, तो वो इसीलिए यूज किया क्योंकि उसकी अवेलेबिलिटी ज्यादा थी, या फिर कोई स्पेसिफिक रीजन था उसके पीछे?
नहीं, वही स्पेसिफिक रीजन वही ना कि वो उसका फ्रीजिंग पॉइंट -89 डिग्री सेल्सियस है और हमारे क्लाउड चैम्बर में वो उतना तो टेम्परेचर अटेंड नहीं हो रहा है नेगेटिव में, तो वो फ्रीज नहीं होगा. कोई दूसरा
तो
अल्कोहल भी
इसे
यूज कर सकते हो आप, इथेनॉल भी यूज कर सकते हो, मिथेनॉल भी कर सकते हो, लेकिन उसका कॉन्सेंट्रेशन कितना है, उसका फ्रीजिंग पॉइंट कितना है, वो सब मैटर करता है यहाँ पे. तो इसलिए मैंने अल्कोहल यूज किया और वो प्योर होना चाहिए, अच्छे से अच्छा 90% से ज़्यादा उसकी प्योरिटी होनी चाहिए. और फिर हाँ, तो आप डिटेक्ट उसका वेपर फॉर्म अगर डेंस भी फिर दूसरा भी पॉइंट है कि आपको जो अल्कोहल जो फेल्ट को आप सोक करते हो वो उसकी डेंसिटी हाई होनी चाहिए. मतलब डेंसिटी हाई मतलब उसका अमाउंट हाई होना चाहिए, सॉरी. उसका इनफ अमाउंट में आपको सोक करना रहता है, क्योंकि अगर थोड़े 20-25 मिनट या 30 मिनट के बाद उसकी कॉन्सेंट्रेशन डिक्रीज होगी तो हमें इतना क्लाउड अच्छा नहीं मिलेगा, और उतना मीडियम जितना डेंसिटी कम होगी उतना डिटेक्शन कम होने लगेगा. इसलिए इनफ अमाउंट में अल्कोहल्स को सोक करना चाहिए फेल्ट पे. तो यहाँ पे जो फेल्ट है वो ये जो पतला सा स्पंज लाइक दिख रहा है वो आप ये कह दीजिए.
नेक्स्ट क्वेश्चन है कि जो म्यूऑन का ट्रैक देखा मैंने,
हाँ.
उसमें एक रेगुलर इंटरवल पे डिस्क्रीट पैटर्न्स दिख रहे थे जो बाकी के ट्रैक्स में नहीं दिख रहे थे, ऐसा क्यों?
दैट
हाँ,
इज
ये रहा।
एक्चुअली ऐसा क्यों, तो मतलब it is a type of interaction that muon is having with चैम्बर. और ऐसा भी हो सकता है कि इन लोगों ने जो फोटोग्राफ लिया है वो इतना जूम किया है तो हमें ऐसा दिख रहा है, लेकिन मेरे आई थिंक दैट इज नॉट अ रीजन, बट ऐसा क्यों हो रहा होगा वो तो अभी म्यून पार्टिकल कैसे इंटरेक्ट कर रहा है गैस मॉलिक्यूल के साथ वैसा दिख सकता है, तो उसके मुताबिक बोल सकते हैं. दैट इज अ डीप समथिंग लाइक बियॉन्ड द स्कोप हियर. So I
एक थर्ड क्वेश्चन ये है कि ज्यादातर पार्टिकल्स ट्रेवल कर रहे थे अलोंग विद द वेपर्स एक डायरेक्शन में, तो कोई ऐसा इतना लाइट पार्टिकल हो सकता है क्या कि वेपर की जो प्रेशर आ रही है उसके ऑपोजिट डायरेक्शन में वो ट्रेवल करे और ट्रैक हमें उल्टे दिशा में जाते हुए दिखे?
मतलब आप ऐसे बोल रहे हो कि वेपर नहीं, पार्टिकल तो उसकी कहीं से भी ट्रैवल करेगा, ऐसा नहीं है कि ऊपर से भी आ सकता है, नीचे से भी आ सकता है, कहीं से भी घुस सकता है एक चैम्बर में. लेकिन फैक्ट इज दैट जैसे भी वो ट्रैवल करेगा, जो डायरेक्शन में ट्रैवल करेगा वो डायरेक्शन में वो आयनाइजेशन करेगा और उसके सराउंडिंग मॉलिक्यूल्स उस पे उसके ऊपर कंडेंस होके हमको वो डायरेक्शन का ट्रैक्स दिखाई देंगे. अब यहाँ ऐसे ट्रैवल करेंगे, ऐसे यहाँ पे जाएंगे तो यहाँ वो डायरेक्शन में ऐसे ट्रैक बनता दिखाई देगा हमको. आप ऐसे बोल रहे हो कि ऐसे गया और हमको ऐसे लगे कि ट्रैक पार्टिकल ऐसे गया?
हाँ,
नहीं नहीं, ऐसा नहीं हो सकता, क्योंकि जहाँ पे आयनाइजेशन ज़्यादा हो पहले होगा वहाँ पे पहले कंडेंसेशन होगा और फिर वैसे प्रोसीड करेगा ट्रैक. इसलिए हम ऐसे बोल सकते कि पार्टिकल यहाँ से यहाँ गया, यहाँ से यहाँ से गया, यहाँ से यहाँ आया. आप one of the questions.
Hello, Jay. Am I audible?
Yes, yes, Michelle.
First of all, I want to congratulate for this amazing talk.
Thank you very much.
મારો ડાઉટ એ હતો કે આગળની સ્લાઇડમાં આપણે જેમ જોયું અલગ અલગ પાર્ટિકલના પાથ હતા તો એમાં એક વી શેપ પાથ હતો તો એ વી શેપ પાથમાં લિનિયર મોમેન્ટમનું કન્ઝર્વેશન થશે?
હા, મોમેન્ટમ તો કન્ઝર્વ થવું જ જોઈએ ને. કેમ નહીં થશે તને એનું કોઈ તર્ક છે તારી પાસે?
કેવી રીતે થશે તો પછી વી શેપ છે તો?
તમે વી શેપ છે તો એમાં નહીં થાય એવું કેમ? એમની વી શેપ છે, માયનું વી શેપ છે, વી શેપ તો અહીંયા બી છે. બટ પાર્ટિકલ્સ પહેલા હતું એ ડીકે થયું. ઓફકોર્સ એનર્જી કન્ઝર્વ થવાની જ છે. અમુક અમુક આ જે ડિસઇન્ટિગ્રેટ થયું તે થોડીક એનર્જી આ કેરી કરશે, થોડીક એનર્જી આ કેરી થશે. એનર્જી
Okay.
કન્ઝર્વ થતી હોય તો મોમેન્ટમને કન્ઝર્વ થવું જ પડે. અને પાર્ટિકલ્સમાં એવું જ હોય ને કે આપણે કોઈ બી ન્યુક્લિયર ફિઝિક્સમાં ભણ્યા કે ભાઈ માસ બંનેનું માસ માઇનસ કરે તો આપણને એનર્જી મળે, ક્યુ ઓફ ધ ઇક્વેશન મળે ડીકે થાય તારે, બરાબર. અને અને અમુક જગ્યાએ ડીકે લિનિયર મોમેન્ટમ કન્ઝર્વ નહીં થતું હતું ત્યાં આપણે એવું કર્યું કે કદાચ બીજો કોઈ પાર્ટિકલ હશે, પાવલીએ જેવી રીતના ગેસ કર્યું ને ત્યાં આપણે ન્યુટ્રિનો ડિસ્કવરી કરી. એટલે ઓફકોર્સ કોઈ બી ડિસઇન્ટિગ્રેશન હોય લિનિયર મોમેન્ટમ કન્ઝર્વ થવું જ પડે. એટલે અહીંયા બી થતું જ હશે. મેં મેથેમેટિકલ કેલ્ક્યુલેશન નથી બતાવ્યા અહીંયા, બટ ઓફકોર્સ થતું જ હોય કારણ કે કોઈ બી ડિસઇન્ટિગ્રેશન છે આ બધા રિટર્ન ડિસઇન્ટિગ્રેશન છે. આ બધાના ઇક્વેશન હશે કે ભાઈ આ પાર્ટિકલ આમાં ડીકે થાય અને આ ન્યુટ્રોન પ્રોટોન નીકળે અને આમાં આની હાથે ડીકે થાય અને આ પાર્ટિકલ નીકળે આટલી એનર્જી નીકળે. બટ મેં અહીંયા નથી રાખ્યું એ સેન્ટ્રલાઇઝ અહીંયા કે ભાઈ અહીંયા કારણ કે એ કરવા જાઉં તો પછી થોડું વધારે લાંબુ થઈ જાય.
ઓકે, મને મારો ડાઉટ ક્લિયર થઈ ગયો. મને લાગ્યું હતું કે પાર્ટિકલ એની ડાયરેક્શનમાં મને ભૂલ થઈ ગઈ હતી. નાઉ ઇટ ઇઝ ક્લિયર. થેન્ક યુ.
આમ જાય છે. થેન્ક યુ. બીજું કોઈ? Any doubts? Any feedback? If you want anyone to give feedback, then also they can give. So no more questions.
मुझे लग रहा है कि अब कोई व्यूअर्स को क्वेश्चंस नहीं है. अगर फिर भी कोई व्यूअर्स को क्वेश्चंस हो तो वो जय का ईमेल आईडी दिया दिख रहा है स्क्रीन पर, उसमें ईमेल करके पूछ सकते हो, या फिर
हाँ, श्योर श्योर.
यूएसएफ को भी ईमेल कर सकते हो.
यस यस.
और जो भी व्यूअर्स अटेंड किए अपना टाइम निकाल कर, जो भी जिज्ञासु व्यूअर्स थे वो सब कुछ बोल सकते हैं. थैंक यू. और ऐसे फ्यूचर प्रोग्राम्स भी अटेंड करते रहिए. और क्योंकि यूनिवर्स साइंस फोरम एक वॉलंटरी ऑर्गेनाइजेशन है तो आप भी मेंबर बने हमारा, और साइंटिफिक एटीट्यूड को आगे ले जाने के लिए साथ दें हमारा. थैंक यू
वेरी मच. और आप फीडबैक भी प्लीज़ सेंड करना. मेरे ये ईमेल आईडी पे आप फीडबैक सेंड कर सकते हो, या फिर आपको जो मेल में गूगल लिंक मिली थी उस पर आप रिप्लाई भी कर सकते हो कि फीडबैक आपको कैसा लगा. तो ये क्या मुझे हेल्प करेगा कि मुझे कैसा मतलब और अच्छा होना चाहिए था. यू कैन tell my negative points also, that are most welcome than positive ones, and that is what I need from you. If you really enjoyed, please I will not say like, share and subscribe, but I will say please send the feedback. Thank you very much. તો દિલીપભાઈ,
હા હા જય.
શું કરું છે? એન્ડ કરી દઉં?
હા
સારું, ચાલો આવજો. જય શ્રી કૃષ્ણ. બાય બાય. જેટલા બી આવ્યા તમામ માણસોને મારા પ્રણામ. चलो बाय बाय. बंद करूं?